So, the next topic which we are going to discuss is colligative property. We have already learned that the vapor pressure of solvent in a solution is less than the vapor pressure of pure solvent, and this relationship is given by the Rolle's law. The vapor pressure of solvent in solution is given by mole fraction of solvent multiplied by vapor pressure of pure solvent. Of course, the change in vapor pressure can be written as vapor pressure of pure solvent minus vapor pressure of solvent in solution, and replacing P1 from here, we are going to get P1 0 minus x1 P1 0, which is equal to P1 0 1 minus x1, and we know this x1 is the mole fraction of solvent. So, 1 minus x1 is the mole fraction of solute. So, we get P1 0 x2. In the binary solution, x2 is the mole fraction of the solute, and if there is a more than one component is available is there in the solution, then this is the mole fraction of all the solutes. Basically, we are going to add mole fraction of each and every component and then add it, and that we are going to call it x2. So, delta P is directly related to x2. We can write this as delta P divided by P1 0 equal to x2. x2 is the mole fraction of solute present in the solution, and this x2 can be written as we have already learned, the moles of solute divided by total number of moles present in solution, that is moles of solvent plus moles of solute. Okay. And then doing subtracting and delta P, we can also write this whole equation as delta P we have defined up here, P1 0 minus P1 divided by P1 0, and subtracting the denominator from numerator, we are going to get N2 divided by N1 equal to P1 0 minus P1 divided by P1. And this equation can be used to determine the molecular weight of unknown solute. If we do not know what is present in the solution, which solute is present, we can use this equation to calculate the molecular weight of solute as following. So, N2 is the number of moles of solute. So, this is defined as the weight of solute divided by molecular weight of solute divided by weight of solution, weight of solvent present in the solution divided by molecular weight of solvent. We already know the information, this weight of solvent present in the solution, and we can use this information to calculate the molecular weight of solute. Okay, let us do an exercise. Okay. So, this is an example from the textbook. The example, I am going to read this problem. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. Okay, so for benzene we are given vapor pressure of pure benzene, that is P10 at a certain temperature is 0.850 bar. All right. In a non-volatile, non-electrolyte solid weighing 0.5 gram. We do not know what solute is this. We are adding 0.5 gram of this solute in the benzene. Now, how much benzene? 39 gram of benzene. So, we are given mass of solute, and we are dissolving this unknown solute in 39 gram of solvent. And since it is benzene, we know the molecular weight of benzene. Molecular weight of benzene would be 12 into 6 C6 plus H6, that is 6, so 78. So, now the vapor pressure of the solution then after of this solution is vapor pressure of the solution is 0.845 bar. This is a non-volatile solute, so there is going to be no contribution from the solute. So, this whole vapor pressure is coming from the benzene. Now, we can just the formula is given right in front of us. So, P10 minus P1 is simply we subtract this and we get 5 into 10 minus 3 bar divided by P1, that would be P1, that is 0.845, and that is equal to weight of solute, which is given 0.5 gram divided by molecular weight of the solute divided by weight of solvent, that is 39 gram divided by molecular weight of solvent, that is 78. So, I can calculate the molecular weight of solvent now easily using this formula. So, that would be so I am going to take molecular weight to other side and bring all the information to other this side. So, I am going to get 0.845 divided by 0.005 and that is going to give me the molecular weight. So, molecular weight of unknown solute is simply 169 gram per mole. So, we have used this lowering in the vapor pressure to calculate molecular weight of unknown solute. If we have some unknown pure compound and we want to know what it is, and if we can find a solvent in which it can dissolve, a known solvent in which it can dissolve. So, we are just going to dissolve some known amount of this known solute in this solvent, and if we can calculate the vapor pressure, and that is it, we can know this molecular weight, and molecular weight will may give you some information about what this compound might be. Okay. Okay, next topic which we are going to discuss is elevation of boiling point, and at this point I want to spend a little time to discuss what is phase diagram of a pure solvent. So, okay, let us see. If I have a closed flask, okay, and this is evacuated, there is nothing in there, it is a pure very good vacuum, and in this I introduce some of the solvent. Okay, so I have a solvent, and we have learned in the previous class that this solvent is going to evaporate, okay, and it this evaporated, the solvent from the liquid phase is going to go into this vapor phase. and we have learned that let us say this is a compound A in a liquid phase and goes to gaseous phase, and this is a dynamical equilibrium, and it will reach equilibrium, and at this point whatever is the pressure exerted by this gas on the surface of this liquid, that will be called vapor pressure. Okay, in this container we have only the pure solvent and its vapor, nothing else, because we started with a empty flask, a evacuated flask. So, this pressure on the solvent, on the liquid solvent, is due to its own vapor, and this is exactly called vapor pressure. Now, if I start increasing the temperature, if I start providing some heat to this system, as I am increasing the temperature, of course, there would be tendency to for the molecule solvent molecule to escape from liquid phase into the gaseous phase, and every time there would be a new dynamical equilibrium as we increase the temperature, and the vapor pressure would keep on increasing. And if I plot simply temperature versus this pressure exerted by the solvent vapor on the liquid, that pressure, then I am going to get a typical curve like this. So, it will the pressure is increasing as temperature is increased, and we start at a point, because below this point the liquid will freeze. So, we will get a a curve between solid and gas, not the solid and okay. All right, now, so this is a curve for pure solvent. Now, what would happen if I add some solute into this? Again, I am going to do the same experiment, and I am just going to measure the pressure exerted by the solvent molecule on the solution. But the solute which I have added is non-volatile. So, it is not going to contribute to the vapor pressure or to the pressure exerted over the solution. But now, there is going to be decrease in the vapor pressure at a given temperature. If the vapor pressure at a given temperature is for the pure solvent was P10, now it is going to be x1 P1. Okay. So, now I am going to just plot this P1 as a function of temperature. So, this quantity multiplied by x1, and I am going to get a curve something like this. So, let us say I was at this temperature. So, for pure solvent, this is the vapor pressure. As I added some solute, now the new vapor pressure is this, and this is basically delta P, where delta P we have just defined is P10 x2. As our temperature increase, this is going to be the delta P, and if you keep on increasing the temperature, this is going to be the delta P. Now, what is the normal boiling point? Normal boiling point is when the vapor pressure P10 becomes equal to 1 atm. If I have left this container open at 1 atm at the normal boiling point, the external pressure and the vapor pressure becomes equal and it will simply boils. I mean all the it will keep on continuously boiling and this gaseous molecule will simply keep on escaping. So, there would be a complete boiling and it will just everything will escape. Okay. So, let us assume that this is 1 atm. So, this is the normal boiling point. So, let me clean this figure a little. So, this is 1 atm, this is the vapor pressure at this temperature, this is the normal boiling point and at this temperature the vapor pressure is 1 atm and this is the normal boiling point. Okay. Now, what would be the normal boiling point for the solution? The solution curve is this. This is the vapor pressure of the vapor pressure curve of the solution. Now, this curve is going to have a vapor pressure of 1 atm at this point. And this is the boiling point for the solution and this is the boiling point for our solvent and this difference delta T is the increase in the boiling point increase in the boiling point of solution with respect to the pure solvent. Now, few points to note. This curve is I am simply plotting using this information. Okay. So, it depends on this curve which is P10 and mole fraction of mole fraction of solvent. So, this curve does not depend upon the properties of solute at all and the change in delta T depends upon the property of this curve, in fact, the slope of this curve at this point and this concentration x1 or related to x2, x1 and x2 are related simply by x2 is equal to 1 minus x1. So, it does not this property delta T as I defined here is proportional to simply the concentration and there is a proportionality constant which is called Kb, which is basically is called molar boiling point elevation constant and this constant depends upon only the properties of the solvent, not on the solute, as it is very clear from that figure. Okay. So, now we can use this property also to calculate about unknown solute. Constant Kb is specific to a solvent. So, let me rewrite this and now let us try to, and this m is the molality of solute in the solution. Okay. Let us do one example. Okay. Here I read 18 gram of glucose, 18 gram of glucose, that is C6H12O6 is dissolved in 1 kg of water, in 1 kg of water. At what temperature will boil At what temperature will water boil at 1.013 bar, and Kb for water is 0.52. So, when we are just asked to calculate delta T. To calculate delta T, I need Kb and molality. Kb is given right here, and I need to calculate molality. What is the definition of molality? Molality is defined, which we have already discussed, moles of solute. So, moles of solute, that is N2, divided by weight of solvent in kg. Okay. So, to calculate this, I need some moles of solute. I am given 18 gram divided by molecular weight of glucose. So, that would be 72 plus 12 plus 96. So, 6, 8, 10, 110, 11, 18, 180 divided by weight of solvent, which is water, and we have given 1 kg. So, it is simply 0.1 molar solution. And now, I have all the information, and I have Kb, I have m, and I can calculate delta T easily. So, delta T is going to be 0.52 into 0.1. So, that is 0.052. So, initially the water was boiling at 100 degree, now it will boil at 100.052 degrees centigrade. So, now we were given the information about glucose. If we do not know about the solute, let us say we are dissolving some unknown solute, then we can use the same information to calculate the molecular weight of solute. Okay, let us do one exercise. Okay. The boiling point of benzene is 353.23 Kelvin. So, we are given a normal boiling point of benzene, that is 353.23 Kelvin. When 1.80 gram of one non-volatile solute, 1.80 gram. So, that is solute, weight of the solute dissolved in 90 gram of benzene, 90 gram of benzene. So, that is solvent. The boiling point is raised to 354.11 Kelvin. Calculate the molar mass of the solute. Kb for the benzene. This constant for the benzene is given as 2.53 Kelvin kg per mole. Okay. So, this information is given, and now we are going to use the formula which we have already seen, that is delta T is equal to Kbm. Okay. Let us see, delta T is already given, that is we are given the boiling point of the pure solvent, this is the boiling point of the solution. So, delta T would be simply the difference. So, delta T is equal to, the difference would be 0.88 Kelvin, which is equal to Kb. Kb is also given 2.53 multiplied by molality. Now, to calculate molality, the definition of molality is moles of solute divided by weight of solvent in kg. Okay. To calculate the moles of solute, we know the weight of solute, which is 1.80 gram, divide that by molecular weight of solute divided by weight of solvent, which is 90 gram, but we have to use that in kg. So, divide by 1000. Now, we have all the information, we just plug in this information in here and we get our equation. So, equation is going to be 0.88 Kelvin is equal to 2.53 into 1.80 into 1000 divided by 90 into molecular weight of the solute. So, we can calculate this. So, molecular weight is going to be 2.53 multiplied by 1.80 multiplied by 1000 divided by 90 divided by 0.88. So, we are going to get 57.2. So, molecular weight we are going to get is 57.5 moles gram per mole. So, that way we can calculate the molecular weight of this unknown solute. Okay. The next topic which we are going to discuss under this subject is depression of freezing point. As we have elevation of boiling point, in the same way we have a depression of freezing point, and this can be understood by the same diagram which I just plotted. Okay. So, this is the phase diagram between liquid and vapor. At some temperature the liquid is going to freeze, and below that we have a phase diagram for solid and gas, and of course, we can have a phase diagram between solid and liquid. So, at this point the liquid is going to freeze. If I keep on decreasing the temperature, in this direction the temperature is increasing. So, in this direction temperature is decreasing. At this point the liquid will freeze, and this is the vapor pressure of pure solvent. Now, I have the curve for the solution as I plotted earlier, and the curve would something look like this. So, initially the boiling, this was the 1 atm line. So, this was the boiling, this is the change in the boiling point, and the same way we are going to have a change in freezing point. So, this was the normal freezing point, and this one is the freezing point of the solution. And again this this line does not depend at all on the property of the solute, it depends only on the concentration and on this line, and this how much shift is going to take place will depend on the curvature of this line. Okay. And again we get the similar formula, that is delta Tf is equal to Kf multiplied by molality of the solution. Okay, where Kf is constant, which is called freezing point depression constant. Okay, this is again same kind of formula, and this is very important. This is very important for aquatic life. In a polar region where temperature can go many degree below the freezing point, we still the water is not going to freeze due to very high concentration of salt in water, in sea water, and that will that is the reason that aquatic life, marine life can survive. Okay, and the same kind of formulation we can do, and of course, Kf and Kb is related to the property of this curve. Kf related to property of this curve, as I said, the it depends upon the curvature of this curve. Kb depends on the curvature of this curve, and this curvature is depends upon this curvature will depends upon the enthalpy of freezing, curvature of this curve will depends upon enthalpy of vaporization, and Kb and Kf has the formula and which can be written as Kb is written as gas constant multiplied by molecular weight of solvent multiplied by boiling point square divided by 1000 multiplied by enthalpy of vaporization. And same way I can write Kf as R into molar mass of solvent multiplied by freezing point into squared divided by 1000 into delta the enthalpy of fusion. Okay. Let us do some exercise based on this concept. Okay. The example is as follows: 40 gram of ethylene glycol is mixed with 600 gram of water. Calculate A, the freezing point depression, B, the freezing point of the solution. So, we are dissolving 45 gram of ethylene glycol. 45 gram of ethylene glycol, that is C2H6O2 in 600 gram of water, 600 gram of water. He is asking delta Tf and Tf, the change in the freezing point and what is going to be the freezing point of this solution. Okay. To do this problem, we also need Kf and we need the Kf of water, because we need the freezing point constant, freezing point depression constant only for the solvent, and that is given in this table, and that is delta the Tf Kf for water is 1.86 Kelvin kg per mole. Okay. So, now I have all the information as required. So, delta T, that is what we need to calculate, delta Tf, which is equal to this constant multiplied by molar concentration, and we need to calculate the molar concentration. Again, going by the definition, molar concentration is moles of solute. So, moles of solute would be 45 gram divided by molecular weight. So, molecular weight is 24 plus 6 plus 32, 62 divided by. So, this is the moles of solute divided by the weight of solvent in kg. So, that is 0.6. So, if I plug in all these numbers, 45 divided by 62 divided by 0.6, I am going to get, okay, or I am going to get this as a 1.2, and this is plugged in this equation, which is 1.86 into 1.2, and I am going to get a final answer as 2.2 Kelvin. So, what is going to be the freezing point of this solution? We know the water freezes at 0 degree centigrade, or so this solution will freeze at minus 2.2 degree centigrade. Okay, let us do another exercise. Okay, let me read. 1 gram of non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 Kelvin. So, the benzene is the solvent and the delta T is 0.4 and the mass of the solute is 1.00 gram. So, 1 gram of non-electrolyte solute dissolved in 50 gram of benzene. So, mass of solvent is 50 gram. The freezing point depression constant for benzene is 5.12 Kelvin kg per mole. So, we are given TF also, which is 5.12 Kelvin kg per mole. Find the molar mass of the solute. Okay. So, we are again going to use the same formula. So, we are given delta T, which is 0.4, Kf is given 5.12 and we need the molality. But molality is again moles of solute, which is 1 gram of solute divided by molecular weight of solute. Okay. So, this is moles of solute divided by weight of solvent in kg. So, this would be 0.05. So, we can use this relation right here and we can calculate the molecular weight. So, the molecular weight is going to be 5.12 divided by 0.05 divided by 0.4. So, answer comes out to be 256. So, the molecular weight of unknown solute is 256. Okay. So, let us do some more example from in text problem. Okay. Let me read the question. Vapor pressure of pure water at 298 Kelvin is 23.8 millimeter Hg. 50 gram of urea is dissolved in 850 gram of water. Calculate the vapor pressure of water for this solution and its relative lowering. Okay. So, we are given vapor pressure of pure water at 290 Kelvin. So, P10 is 23.8 millimeter Hg. 50 gram of urea is dissolved. So, the solute is urea. So, weight of urea is 50 gram. Since we will need the molecular weight, so I am just going to write urea molecular formula of urea, that is NH2CO NH2. So, 50 gram of solute, this solute in 850 gram of water. Is asking first the lowering and the relative lowering, delta P by P10. So, we are going to use the formula which we have discussed. Delta P is going to be P10 x 2. Okay. So, P10 is given. So, that is 23.8 into x 2 mole fraction for solute. So, mole fraction x 2 is N 2 divided by N 1 plus N 2, and we can ignore N2 with respect to N1, that we can see in a minute. So, N2 is going to be 50 gram divided by molecular weight. So, that is 14 to 16, 16, 32, 48, 12, 60, 60. Okay. And N1, we have 850 divided by 18. So, you can see that this is approximately order of 1 and this is approximately order of around 50. So, if I ignore N2 with respect to N1, I am making ignoring a quantity 1 with respect to 50. So, this is approximately 2% error, which is acceptable, even though I do not have to ignore. Just for the making the calculation simpler, we usually ignore that quantity, and so x 2 is 50 and 2 50 by 60 into 80 850. So, I put that quantity right here, 50 into 18, 60 into 850. Okay, and let us use the calculator and see what we get. 3. So, the loading and vapor pressure is 0.42. And now, what about this quantity? This is nothing but x 2, which we have already calculated that. So, x 2 is right given here. Okay. So, we can handle this problem quite easily. Okay, let us attempt the next problem. Okay, let me read the problem. This is in text question 2.10. Boiling point of water at 750 millimeter Hg is 99.63 degrees centigrade. How much sucrose is to be added to 500 gram water such that it boils at 100 degrees centigrade? Okay, so, this is a problem of elevation of boiling point. So, the boiling point of pure solvent is given as 99.63 degrees centigrade at 750 millimeter Hg. Of course, one might wonder how come this boiling point of water is changing. We know as we go at the higher elevation at some hill station, the boiling point of water changes. It boils at lower temperature, and that is due to something the external pressure. At 1 atm, the normal boiling point is defined at 1 atm. So, at 1 atm, water boils at 100 degrees centigrade, but at 750 millimeter Hg external pressure, water will boil at 99.63 degrees centigrade. Okay, and then how much sucrose is to be added? So, we are adding sucrose to be added to 500 gram of water. So, weight of solvent is given, that is 500 gram of water, such that it boils at 100 degrees centigrade. So, boiling point for the solution is 100 degree centigrade. Okay. So, we are going to use the familiar formula, that is delta T is equal to Kb multiplied by molality. Of course, the Kb is listed at a normal boiling point, and we have seen the Kb is a function of temperature, but we are not going to wonder we are not going to wonder about that, because this is quite close to 100 degrees centigrade. So, we are going to assume Kb is same for this system and the when the temperature is 100 degrees centigrade. Okay, so delta T. So, delta T is given right here, the difference between the boiling point of the solution minus boiling point of solvent, that will give me delta T, that is 0.37 degree centigrade or Kelvin, equal to Kb for water. We know it is listed in one of the tables, and that we can find it. Kb for water is 0.52. 0.52, and m is molality. So, the definition of molality is, let us go to our ABCD. Definition of molality is moles of solute divided by weight of solvent. So, weight of solvent is given right here, 500 gram in kg, 5.5 kg, and the moles of solute. So, we need to figure out what is the weight of solute. So, to convert the weight of solute to moles of solute, we need the molecular weight of sucrose. The sucrose is C12H22O11. Okay, so, the weight of this would be 144 plus 22 and oxygen 11, 16 into 11, 176. So, this would be 4 to 6, 12, 1, 8 to 10, 14, 342. So, if weight of solute is W2, then the moles of solute is simply going to be 342, and we can put that information right here. So, moles of solute is W2 divided by 342 divided by weight of solvent in kg, that would be 0.5. We take this information and put it right in here, W2 divided by 342 into 0.5. One equation, one unknown, we solve it and we will get the answer. Okay, let us use the calculator. 0.37 multiplied by 342 multiplied by 0.5 divided by 0.52. So, answer comes out to be approximately 121.7 gram. Okay. Okay, now let us look at some problem from the end of the chapter. So, the next problem which we are going to discuss is 2.18. Let me read it out. Calculate the mass of a non-volatile solute, molar mass 40 gram per mole, which should be dissolved in 114 gram octane to reduce its vapor pressure to 80%. Okay. Calculate the mass of non-volatile solute. So, we are asked the mass of non-volatile solute, whose molar mass is given, molecular weight is 40 gram per mole, which should be dissolved in 114 gram octane. So, mass, the solvent is octane over here. So, mass of solvent is 114 gram and the solvent is octane, that is C8H18. And to reduce the vapor pressure to 80%. So, if original vapor pressure of octane is P10, then the vapor pressure of solution should be 80% of that. So, this is the information given to us. Okay. We know from the Raoult's law that vapor pressure of solution is equal to mole fraction of solvent multiplied by vapor pressure of pure solvent. So, just by comparison we know x1 is equal to 0.8. All right, and let us see what is the definition of x1. We need to figure out m2. So, the definition of x1 is moles of component 1, that is solvent, divided by N1 plus N2, binary solution. So, moles of solvent plus moles of solute, total moles. Okay. So, we need N1 and N2. Okay. So, N2 we can figure it out right there as an unknown, that is M2 divided by 40 gram per mole. So, weight of the solute divided by molecular weight of the solute. So, that will give me moles of solute. What about N1? For that we need the molecular weight, and that would be 96 plus 18. Oh, that comes out to be 114. So, that is convenient. So, N1 is simply 1. Take this information, put it in this equation, and that would be 1 divided by 1 plus M2 by 40. Now, simply doing a little bit of algebra, just subtracting numerator from denominator, we will get 0.8 divided by 1 minus 0.8 equal to 1 plus M2 by 40 minus 1. So, that is 0.8 divided by 0.2, that is 4. 4 is equal to 1 by M2 by 40. So, this is now a simple equation to solve. M2 is simply coming out to be 40 by 4. So, the answer is simply 10 gram. Okay. Let us discuss one last problem for this section. Okay. 2.19, the next problem. A solution containing 30 gram of non-volatile solute, exactly 90 gram of water has a vapor pressure of 2.8 kilopascal at 298 Kelvin. Further, 18 gram of water is then added to the solution, and the new vapor pressure becomes 2.9 kilopascal at 298 Kelvin. Calculate molar mass of the solute, vapor pressure of water at 298 degree Kelvin. Okay. So, basically we have two solutions. We have to work with two solutions. The solution 1 is 30 gram of non-volatile solute in 90 gram water. 90 gram water, and for this solution the vapor pressure is 2.8 kilopascal. And we have the second solution. The second solution is just prepared by adding 18 gram of water in this solution. So, the amount of solute remain same. This is still 30 gram of solute in, now we have added 18 gram of water. So, amount of water becomes 108 gram water, and the resultant solution has a vapor pressure of 2.9 kilopascal. Okay. Now, he is asking what is molar mass of solute. So, molecular weight of solute, and he is asking vapor pressure of water. So, vapor pressure of pure solvent. So, we have two unknown, and we can get two equation from these two solution. So, let us go back to our Rolle's law. Rolle's law is P1 is equal to x1 P1 0. Okay, and what is x1? x1 is moles of component 1 divided by total moles. Binary system, only 2 components. Okay, and we are given only masses. So, we need to convert this information, the mass given, to moles. Okay. So, 90 gram of water. So, that is the molecular weight of water is 18. So, we have simply 5 moles. So, N1 is 5. What about N2? N2 we are given 30 gram of solute and the molecular weight is unknown. That is what we have to figure it out. So, we will just put moles of solute in terms of molecular weight of solute. So, that would be 30 gram divided by molecular weight of solute multiply by okay. So, this is x1. Now, we can take this and put it in here and we get P1 is equal to 5 divided by 5 plus 30 the molecular weight of solute multiplied by P1 0 and that is equal to 2.8 kilopascal, and so we are going to calculate P1 0 also in kilopascal. Now, same equation we can set it up for the second solution and that would be 2.9 kilopascal is equal to x1. So, in this case now to calculate x1 the amount of water present is 108 gram and that is conveniently is 6 moles. So, N1 is 6. So, x1 is going to be 6 plus 6 divided by 30 by molecular weight of solute multiplied by P10. So, we have 2 equations and 2 unknown. Simply divide equation 1 by equation 2 to remove one of the unknown. So, we get 2.8 divided by 2.9 and that is equal to 5 divided by 5 plus 30 divided by molecular weight of solute divided by this whole thing. So, that would be multiplying 6 plus 30 by molecular weight of 2. So, now this equation has one variable, one unknown. Okay. So, we can set it up. This is easily 6 plus 30 by m the molecular weight of solute divided by 5 plus 30 divided by molecular weight of 2 is equal to 2.8 into 6 divided by 2.9 multiplied by 5 and this is 2.8 multiplied by 6, 16.8 and 2.9 multiplied by 5 that is 14.5. Okay. Now, again subtracting numerator from denominator, we can simplify the whole thing and we will get 6 plus 30 divided by molecular weight of solute divided by 5 plus 30 molecular weight of solute minus 6 minus 30 molecular weight of solute equal to 16.8 divided by 14.5 minus 16.8. So, this simply cancels out and we get from here 6 plus 30 divided by molecular weight 2 divided by minus 1 equal to 16.8 divided by minus 2.3. Now, this can be solved. 16.8 divided by 2.3 is going to give me 16.8 divided by 2.3 is equal to 7.3 minus 7.3 minus goes to other side becomes plus, 6 goes to another side becomes 1.3, and I get 30 divided by molecular weight is equal to 1.3. So, molecular weight becomes simply 30 divided by 1.3. So, we got our answer, that is 30 divided by 1.3. So, it is approximately 23 within the rounding error. Okay, now, we have molecular weight. So, using this I can put all this information right in here, and I can calculate P10. Okay, so that I will leave it as a exercise, should not be a problem at all to finish this problem.